In the 1970s and 1980s, theoretical physics was reaching for something grand, a unified theory of everything. At the heart of this quest emerged a radical idea. All fundamental particles are not points, but vibrating one-dimensional objects called strings. And so, string theory was born. These strings could vibrate in different modes, giving rise to the different particles of the Standard Model: photons, electrons, quarks, as well as to gravitons, the hypothetical carriers of gravity. It was beautiful, elegant, a framework that could unite quantum mechanics with general relativity, two pillars of physics that had never fully agreed. But there was a problem. In the early versions of string theory, particularly bosonic string theory, physicists kept encountering a disturbing mathematical anomaly. The theory predicted the existence of tachyons. Not virtual hints or symbolic signals, but actual, faster-than-light particles embedded in the fundamental spectrum of the theory. This created a dilemma, because tachyons in this context implied instability. The ground state of bosonic string theory wasn't stable. It was perched precariously on top of a potential energy hill. And like any unstable system in physics, it would want to roll down into a more stable state. So what did that mean for string theory? Was it fundamentally broken? For some time, this was a serious crisis. Many physicists began to doubt whether string theory could describe reality if it demanded particles that violated causality and undermined the very fabric of time. But as with many scientific revolutions, this apparent flaw became a window into deeper truth. The tachyon was telling them something. In this view, the presence of a tachyon in bosonic string theory was not a bug, it was a clue. It meant that the version of space-time being used, the dimensional structure, the vacuum state, was wrong or incomplete. The theory needed refinement, and so came supersymmetry. Incorporating supersymmetry into string theory, which pairs bosons, force-carrying particles, with fermions, matter particles, helped remove the tachyon from the spectrum. This led to superstring theory, a more stable and mathematically robust framework. Now, with supersymmetry, 5 different versions of superstring theory emerged, each consistent in its own way, and none featuring unwanted tachyons in their low-energy states. But this raised a new puzzle. If there were 5 different consistent theories, which one described our universe? The answer came in the mid-1990s with the rise of M-theory. This mother theory suggested that all 5 string theories were actually different aspects of a deeper, 11-dimensional framework. The tachyon crisis had helped spark a chain of theoretical upgrades and brought physicists closer to a unified vision. But even with tachyons removed, they didn't disappear from the conversation. In fact, in certain conditions, particularly involving D-branes, higher dimensional objects in string theory, tachyons still emerge. These tachyons indicate that a configuration of branes is unstable and will decay into a more stable arrangement, similar to radioactive decay in nuclear physics. This leads to the concept of tachyon condensation on D-branes, a process through which unstable brane structures dissolve or morph into lower dimensional states. In a way, tachyons became tools, not threats. They help physicists understand which configurations of space, strings, and branes are physically viable, and which are doomed to decay. But they also hinted at something else, that the universe might be more dynamic and flexible than we ever imagined. Rather than being static, space-time, and the objects within it, might constantly evolve through hidden processes driven by field instability. Tachyons in this light aren't violations of physics. They're instruments of cosmic refinement. In some versions of string cosmology, it's believed that our universe might have started as a tachyonic field collapsing from instability. The Big Bang, in this view, could have been a phase transition, the resolution of a tachyonic state into a stable, expanding universe. This is a radical but compelling idea, that the ultimate engine of cosmic creation wasn't stability, but instability resolving itself. And perhaps the tachyon, this once feared ghost particle, is the mathematical fingerprint of that transition. Even today, tachyonic states are used as test beds in simulations and as probes into the mysterious string landscape, a vast space of possible vacuum configurations allowed by string theory. Each vacuum has its own physical constants, laws of physics, and particle spectra. Some may have tachyons, others may be perfectly stable. We happen to live in one that seems stable, but are others out there? Are tachyons still lurking in unreachable corners of the multiverse? Or are they still active in our own universe, guiding unseen processes in dimensions beyond our perception? No one knows for certain. But what is clear is this: without the tachyon, string theory would never have evolved into its modern form. It forced physicists to question assumptions, abandon broken models, and imagine a universe where time, space, and matter arise from vibrating strings and higher-dimensional membranes. And perhaps, just perhaps, the tachyon still has more to teach us.